So hi everyone, welcome to today's workshop with Fluence, and this is the first workshop in the Hack the System hackathon that we're running over the next sort of 10 weeks. And yeah, this hackathon is going to be led by the Fluence team, which consists of Anna, the community lead, and then Alexey, Dmitry, and Bernhard. So they'll all be here to walk you through Fluence today, the technology, and answer any questions you might have in relation to the hackathon. So just a bit more in general about the hackathon. We start off with the 5-week learning period where you are allowed to hack, but we host workshops with the sponsors. We have general introduction to blockchain coding workshops, just for everyone to get to grips with blockchain if you maybe haven't developed on it before, and a chance to learn a bit more about our sponsors' technology like we have today. In terms of support throughout the hackathon, we do offer one-to-one kind of advice sessions. So if you are in need of one of those, we're happy to have. We usually try and encourage 2 or 3 throughout the hackathon with each team, just to give advice on the sponsor challenges, how you can improve your product, and the best kind of the attributes we look for in the winners of the hackathon. So it's a really good session to set up if you would like to. In general, the hacking should start by around the end of March, and the submissions are in early May, and then the judging and the final event will be in mid-May. And obviously we have the upcoming events wise, we have the Stellar workshop this Friday, and we have a general introduction to blockchain event next Tuesday, and next Wednesday, the 10th, we have the workshops with Skynet and Vega. But without further ado, I'd like to hand over to Alexey from Fluence, and they're going to run the workshop today.
Oh, thank you. Let me share the screen. Oh, can you please allow me to share the screen?
Sure, Anthony, could you?
Yeah, try now.
Yep. Cool. I shared the link to the chat here in Zoom. It's a pretty long one, but still, go there to follow the workshop with me. There are useful links and the code and stuff. And if you do that, that will be easier for you to follow. But though you don't need to follow and repeat with me everything. If you don't want to, it will still be okay and interesting for you. So feel free to choose any mode that you want to have this workshop on. So first, let's start with the requirements. If you are to follow me, you need to go to the requirements title here and install everything that says here. It's version now. Anyway, so you will need npm or yarn to install JSSDK, JSSDK and FLDist. That's the utility we use to manage Fluence from command line. And all this stuff you will need to develop services in Rust. Okay. It will take some time to install, so especially Rust, and compile all of this. So please do that as early as possible if you are to follow me. And then, sorry for scrolling all around, and then let's take a look at our bounties. We have 3 bounties. First one is to use Aquamarine with existing service. They can be not really clear right now, or well, you don't know much about Fluence, but they will be clear after the workshop. So let me disable those notifications. I have a link here to the Medium that describes the bounties in detail. So let's just review it a little. So the first bounty is called Easy Challenge. You have to use custom air script to query one of the existing services. That should be really, really easy. And you will have $100 per functional submission. It says that you need to dockerize your submission. That's not entirely true. It's optional. You can submit a working repository on GitHub. It has to have some makefile there, or npm script, or sh script, or just in README you have to put instructions on how to run your project, and it should work on the execution of that command. So that's the main requirement for your submission to be considered functional. That's what Dockerized is meant to mean. So the second bounty is medium challenge. It's for $250, and you have to implement and deploy custom service. It can be a service that queries Ethereum, or maybe some other service. It's got to be a custom service, not the one from the workshop, and yeah, custom air too. And the last bounty is to, well, win the hackathon. You have to submit custom service, custom scripts, and custom front end, and you will compete with others for the first place of $2,000 and the second place of $1,000. Same here, it says Dockerized, but it means really that it's got to be working, and it's got to be really, really clear how to run it. So if it's not clear how to run your submission, it won't be, it will be hard for us to judge. So please make it clear how to run. Okay, so refer to this article on Medium for more details, or ask me in the chat. I have a few people, Dmitry and Pavel, today helping me with answering the questions, and Anna too, surely. So please don't hesitate to answer your questions here in chat. And as I said, if you go to this link that I have posted to Zoom chat, you will see a link to the Medium article here at the bottom. Okay, let's scroll all the way up. So to understand what is it like building for Fluence, and why Fluence exists, and how to think about it, I'll start with what you hopefully already know. So I'll start with kind of analogy. So imagine we want to build some, let me zoom a little, I think it's better. So imagine you want to build some kind of simple chat that can add users, add messages, and query users and messages back. And also imagine that you want to have some in-chat comment like search for something in DuckDuckGo. I chose DuckDuckGo here because it's nice. It's a nice service, and it gives you an API to really implement this functionality. So if we are to build such a chat, we will have to start with some backend and its API, right? It can be like an HTTP endpoint, like add users with this instead of a structure, or instead of JSON, just passed as get parameters. It doesn't really matter. Here it's so it's just an idea. The principle will always be the same. You will have some endpoint that is called something like add user, and you will pass their name and ID of the user to add that user there. You will have a query endpoint to get list of users. You will have a add message endpoint to add message with this thing. It will be more clear later, but it's an authorization token, and it's a simple Boolean, so it's true, false, and it works in Fluence that way. And it's really interesting how it works. But anyway, you will have, instead of Boolean, some more complex logic, GBT token or something. Still, you will have add message endpoint, then you will have get message endpoint, and finally query URL endpoint to implement the DuckDuckGo searching functionality. So that's what I would start with when building a simple chat, not on Fluence, but a general traditional client-server application with backend, with API like this, and with front-end with basic functionality like add user, send message, list users in list area, some scrolling thing, and in the input you would be able to type that comment, so it will go to query endpoint. And the same for other functionality. You will have that button add user that goes to the endpoint add user. So it's all really natural, all really familiar to you, I hope. So whenever I want to prototype on an application like this, I usually have to start from more or less from the scratch. I have to have some server listening on some port, some routing logic, something to store data, something to query data. I have to think about how to do this thing and then that thing, and implement all this in my front-end application. And that's always pretty much the same, right? It's always pretty much the same logic everywhere. And a lot of people who start prototyping apps like this, they just repeat what's already been done by others. But why? Why waste human time? If you're surely not the first human to store a list of users and messages in a database, right? And there are already someone who built maybe libraries for that, maybe template repositories that you can start with. But what if someone already has running such components somewhere? How do you reuse them? My cat's going a little bit wild. Anyway, so if you have those components, that backend somewhere running, already wrote it, already compiled it, already deployed it to some cloud or anywhere, how do you use it? How do you find that API? You surely can just Google for it, right? Like, what do you enter even in search field? If you know someone who's running such API, you could contact him directly and ask for access to it. But that's really not a systematic solution. I would like to be able to reuse someone's API if he's okay with that. And I would like to have some discovery around that kind of interaction, right? So it would be nice to reuse code and that's already running and maybe even reuse the state. So for example, if someone like Twitter or Telegram gives me access to their user base in a secure way, in a limited way, and I can imagine that you can prototype your own chat with Telegram API without having to implement the whole Telegram API that's required for a fully functional Telegram client. You just want to query users from there. And imagine that that API is freely available to you and you can connect it to Twitter API somehow, like get users from Telegram and send messages to them to tweet on Twitter. And all that without redeploying the services, without searching for open endpoints, because if Telegram surely has some APIs inside their cloud, but they're not exposed to the public because it's really hard. It's behind the security perimeter, and it's not a traditional way to go and expose your APIs to anyone to use. And that's kind of, I understand why is that, but that's kind of sad. But even if you gather access to those APIs, they're vastly different. You have API from one vendor, it uses XML, other vendor uses JSON, and you have to convert. And where do you convert? How do you compose those different APIs? Do you write logic on front end and get your front end bloated? And if I want to reuse that logic in another app, I have to write it from scratch or copy paste. That's all really problematic. Let's put it that way. So let's reflect on that for a moment. And I will answer how to solve that problem with Fluence. But first, let me talk about what's Fluence. About what Fluence is. So Fluence is a protocol. It's a protocol for peer-to-peer network, where peers, servers or browsers or mobiles or cats, and it is possible to interact between browsers, between mobile devices, between servers. Since it's a peer-to-peer, it's a horizontal network. There are no special roles there. All peers decide what they want to do on their own. So you can host decentralized or distributed applications on Fluence. Every application is a WebAssembly service. So the runtime we use for application is WebAssembly. And applications, they can be hosted on a set of peers, not on a single one. You can scatter the services of your application on several peers and compose them through script language that I will show you and we'll talk about later. Okay, so even though all applications are WebAssembly services, they have access to outside world. If you know about WebAssembly, you could wonder how do you exit sandbox, how do you use network. That's all durable on Fluence. Sorry. Okay, so we have this script language based on PyCalculus, which I will show you, and we will learn how to use it to compose services and how to orchestrate them. But let's first have a mental image of what Fluence is. I think this picture is a good tool to do that. So what do you see here? We have this circle. That's a network. That's Fluence network. That's connected by Fluence protocol. You can see those squares here. Those are the nodes. You can see smaller red dots. Those are the services on the nodes. So I can say that this node here runs 2 services. And those browser icons, those are the clients. And clients want to interact with each other. For example, they want to use chat. They want to send message to chat members and to store it to somewhere durable. So messages can be retrieved later. How it works. So first, since the browser isn't really have ability to receive incoming connections on its own. Imagine you're sitting at McDonald's behind the net, behind all the Wi-Fi limitations and firewalls, you can't receive incoming connections. So to interact with the network, then such clients, they use nodes called relay. Currently, any relay can be used as a node. In the future, you will have to agree with a node if it wants to be your relay. Currently, you can just use any node as a relay. So the fox, the red fox, it wants to send a message to the chat. How does it? It sends a script that says, go to user list service, load the list of users. Those are IDs, peer IDs of those clients. And for each user, go and call a function display message on each of them. So it's not like you're sending a message to each of that client, each of those clients. Not just like that. You're actually calling some API that each client has defined beforehand. So if a client is participating in chat, it defines through JS SDK, it's very simple. It defines the API function that are callable on that client. So in this case, they are participating in the chat, so they define display message function. Display is a service, message is a function. It's really easy. So it's basically a callback. So this client, what it does, it loads, it asks the network to load a list of users in the chat and then call on each of them a callback, a function that will display a new message on their screens. And after, and in parallel to that, all that happens in parallel, And in parallel to that also happens the persistence of the message. So here, in parallel with sending, with calling display message functions on client, we also store message on history service. So what's under the hood? Under the hood, every peer, including browser clients and nodes and others, they have WebAssembly runtimes. You can see that all nodes have at least one WebAssembly runtime. This runtime is used to interpret the scripts, the PyCalculus-based scripts that define the orchestration of the network. So this add message, store message, display message, it's all part of the script. I will show you a little bit later. And it's interpreted in the WebAssembly. So what it means, why we done that, is that WebAssembly is highly portable and it's sandboxed. So you can take this interpreter of the script language and put it anywhere where you can run a WebAssembly runtime. And it will be able to interpret the scripts and basically will be able to participate in the network. And as I said, some nodes, they can also host services, and the services are also run in WebAssembly runtime, in a different one. It's the same runtime, but with different WebAssembly module loaded into it. So Fluence network is this. It's really simple. It's a coordination network that handles routing, that allows you to program the routing and program the way peers behave. So let's take a step back and talk about how Fluence maps to web apps we discussed before. So it's the same in a sense that you can deploy and run backends, and you can provide APIs for other people or for yourself to use. You can execute effects. That means that you can write on disk, you can query network and stuff. You can send requests to your backends and you can receive response. But it's different. It's different because it's a P2P network, not a client-server architecture. And P2P architecture it's more general than client-server. It can implement client-server and more. Instead of having backends as different beasts compiled from different languages to native code, you have services compiled to WebAssembly. Instead of HTTP, you're using Fluence protocol. It's based on Rust libp2p, by the way, which is a really nice library if you're building libp2p networks, I mean P2P networks. You should check it out. And what makes Fluence really outstanding is that requests, they are programmable. You can program routing through scripts. You can say to the network, take this request, put it here, call some function, take result of that function, send the data to another place, then there, then here, and you can call a lot of services. You can call any number of services. You can compose their results. You can transform the results, and you can send data from one service to another, save it to database, read from database, then call some notification service. Anything you can imagine, you can do. So what are the benefits of P2P network? I said that it's a more general architecture than client server. Why? Well, clients, they can communicate directly. They don't need to have servers if they're if they can have a direct connection. They can avoid having servers, or they can use servers as a blind relays that just proxies that just forwards the data from between the clients. Servers of different vendor can communicate. If Twitter or Telegram or other vendor is to expose their APIs to the Fluence network, you will be able to compose them directly, or they will be able to build on one on each other's services. So imagine you have your company developing some services, and you know that a friend from another company is just started developing the same service. Then you can contact him and you can discuss, and you can give him access to your service in a secure way, and he can reuse it without writing their own from scratch. And they don't need to host it. You can host it. You can share already running services between companies. You can do that in private setups. You can do that in your home local network, anywhere. And if you like microservices, and if you really think about it, then microservices are really P2P natives. They communicate directly. They can have some Kafka between them to proxy requests to one another. That's called choreography pattern, but still it's basically a P2P. And what we have also is a built-in peer and service discovery. If you want to reach some node in the network, some client in the network, all you have to know is its peer ID and the peer ID of the relay it connected to. And that's all. You don't need to know IP addresses. It will be automatically discovered through the Kademlia network, through the Kademlia service discovery. And same with services. If you or your friend or someone else deploy the service to the network, all you need is peer ID of the node that this service is hosting and the service ID. So you need peer ID and UUID of the service. And you can call that service. You can inspect its API, you can compose it with other services. So why WebAssembly? Well, WebAssembly, it runs on browsers, on servers, on mobiles. So I guess you can even put it to embedded devices. WebAssembly can provide us with typed interface. So we catch all the nasty runtime errors in the compile time with interface type. This is still in development, that functionality, but we will be there. We already have our own implementation of interface types, which is still in the proposal phase. WebAssembly gives you security sandbox. It's a really simple binary format, so it's easily inspectable and instrumentable. And by design, it doesn't have unlimited access to the operating system it works on. Like native apps. Native apps, they usually can call any syscall. But here in WASM, you have WASI to limit that. You can configure which syscalls are okay for you, which directory is your application if you are to host the node in the Fluence network, then you can configure which apps you allow to run, which binaries on your node you allow them to execute, which syscalls even you allow them to execute. So the major pain that arises from my experience as a backend developer is to compose services. If you have different APIs, you have to write this integration code inside your front-end app or inside your backend service. And it's hard to make it reusable, really, because you can implement it as a library and give nice interfaces to others, but it's really it's really a hard task. It's basically making a library, an internal product, and you have to support it and all that. With Aquamarine, you can compose services without depending on the actual implementation of the services. So it's a different language, it's a different execution environment. You have this script that I will show you already in a moment that controls different services. And you have the services that are written, for example, in Rust and compiled to WebAssembly. In some service, it may use SQLite today, but tomorrow it can be redeployed and use Redis to store its data. And Aquamarine, it doesn't care really. If you change API of the service, you change the API in the script, and you can share that script between different projects. Aquamarine scripts allow you to program coordination and orchestration. You can express many algorithms. You can express Kademlia, and we're already working on porting Kademlia to that scripting language. Currently, we enjoy the Kademlia baked into our nodes, use it, and we took it from Rust lib2p, and it's a great implementation. But we thought, why do we need to bake Kademlia into our nodes? Couldn't they just start and wait for comments? And if those comments tell it how to organize in a XOR topology, in a Kademlia topology, well, they will do that. All you have to do is to allow scripts to manage connection of the nodes, like say to connect to this node, send message to this node. And that's based, and you have to be able to execute functions on different nodes, on different peers in the network. And having those primitives, you can port the complex Kademlia algorithm to the scripting language. That is, and it will be pluggable on each node. So if you need to have different Kademlia network for your own project that will work only on 10 of your nodes or on 50 nodes that you know, or really any different topology, you can have it. You can take the scripts of our Kademlia implementation, you can copy them to you and deploy same services or modified services, and you can compose them and have your own Kademlia. So currently, Fluence Network has just one Kademlia network. And after we port it to Air scripts, you can have tens or hundreds of those networks, or thousands, and they can be totally independent with different logic. If you want to to prototype and try your own custom Sibyl attack defense, you can do that with a simple change in the script. You don't need to have all the code compiled to some node and then go to that node and learn how it works to the ground. I mean, 100%. You can try to change it in little pieces. It's already working. You can try to adjust this script that's responsible for service discovery or for data dissemination. And you can already reuse existing Kademlia services. But it's still a work in progress. We will hope to get there. That's one of our great goals to do that. You can also implement Gossip protocols, Raft consensus, and BFT consensus on Aquamarine. You can have microservices composed in Aquamarine. You can have them in public and private deployments on your local home network, on your work, anywhere. You can have different communication patterns expressed in Aquamarine scripts. You can push notification to browser clients. You can pull data from browser clients periodically. You can send message from one browser to another browser to some node and express any topology with it. And you don't need to receive responses, because when you, if we remember the chat API I showed in the beginning, how do you compose data from get users endpoint with add messages. You have to send a GET request or some RPC request to one of the endpoints, say that will give you a list of users back. You will have it on your front-end application. And then on your front-end application, you will traverse that sequence of users and send each one of them a message. So those are really unnecessary network hops. You don't need to have this data returned to you. You can do it all in one script. You can tell network to do that. You can delegate all that burden to the network. And Aquamarine is reusable. You can, as I already said, it's detached. It doesn't really care about the logic inside the services. So you can reuse the same scripts between different products, between different networks, because coordination is independent from the code on peers. And if someone updated or you yourself updated version of the service and maybe API changed, you just change a little name of the function or some format of the arguments in the script. And that's it. You don't need to redeploy anything because the script is just a text file. You can just run it anytime. And yeah, we have this thing coming soon. It will allow you to reuse whole topologies. It's really hard to express in words. But imagine that you will have a script that for each node in some topology, in some set of nodes or of peers, executes some function on it. And then you say, for that list of peers, execute a function on each of that of the peer in the list. And then you switch list topology to cadenza topology or to raft topology. And then you say, execute, go through the raft, find out, and topology will define that you have to go through the raft, discover all other raft members, check that they are alive, and only then call a function on them. And thus they will be reusable. You can switch one topology to another. But that's work in progress, this reusing topology. I'm really excited about it as a backend programmer because, you know, it's going to be nuts, really. It's really hard to put it in words. And once we have it done, we will have it in the code, and it will be amazing. So what we have now, we have Aquamarine scripting language that's ready for use. We can compose services. Aquamarine scripts, they are currently written in AIR language, Aquamarine Intermediate Representation. That's a low-level language for. I like to think about it as a configuration language for distributed systems. You're not just programming, you're configuring, because it's a very, very simple language. It has like 8 instructions or so, and that's all. It's not a Turing complete language whatsoever. It's really closely correlates with PyCalculus, if you know it. It's a mathematical framework for describing concurrent processes that run in parallel on distributed nodes. And we took that theory and put it into practice with AIR language. Currently, we have Aqua high-level language in development. It's called Aqua, and it will be compiled to that AIR, but it's still in development. We have already a lot of examples done on Fluence that showcase P2P communication, that showcase how to broadcast messages, how to broadcast function calls, how to do authorization, how to talk with Ethereum service, and how to basically implement Oracle, taking data from Ethereum service and processing it in a specific way and put it to other services. You can periodically take, for example, prices from Ethereum nodes or from some API that give you prices, and then put up a service that implements some prediction algorithms and gives you a service that predicts prices. That's all doable on Fluence. So what this script language looks like. This here I have it's the same script, just in text and in a picture. Picture has a nicer syntax highlighting, so let's start with it. So what we have here. This script tells the network to go to some node called relay, call some service called user list, and check if the current user that sent the script is authenticated. If it's authenticated, and the result of that authentication is put into variable status. So this call here is really a function call. You call function is authenticated on service user list, which is hosted on the node relay. And you put result in the variable with name status. So then you go to the history service. For example, it's a chat history service, for example. Could be any other history service, but here it's a chat history. And you call add function, meaning that you want to persist the message into the history service so others can read it later. So it's a persistency layer of your chat application. And you specify two arguments to the function add. First one is message that contains some hello or image or whatever. And the second one is this construction that takes field is authenticated from the status. So status, it's a structure that has that field is authenticated. And it's a Boolean, simple Boolean, but under the hood, we have this security logic implemented for all arguments. I will talk about that at the end of our workshop. And it checks that this Boolean, true or false, it comes from correct service and from correct field. So if you, for example, here you would use status dot is not authenticated, it will fail. Not just because it will be a different value, if it will be still be true, or if you just put here a true, it will fail because it expects the result, this status dot is authenticated, come from this service, from this exact field. We will see that in action, and we will see the authorization failing, and we will fix it. So once we added a message to the database and persisted it, we then go to user list service and ask for all users of the chat. And then we iterate this fold instruction here. It means iterate through the array of users. And for each user, put it into variable named view, and then call chat display function on each of that peer. So from that code, you should be able to see that the view here, it must contain field peer ID. And that's this $sign is the syntax for JSON path. So all this expression and this expression, it's a simple JSON path followed by exclamation mark. We have a documentation on this, documentation on the language, documentation on instructions, documentation on services. So bear with me, we'll go there. You will have links to study it yourself if you want. Oh, I have some problem here with indentation. Let's switch to the text. It's a better identity. So what's happening here? If something goes wrong, return yourself the error. But how? Here on the top level, we have this instruction XOR. What it does is that if this any instruction in that block fails, it will call this block. So it takes two sets of instructions. Basically, it takes two instructions. That's the first one, and that's the second one. If the first one fails, the second one will be called. It's just a simple try catch. This is a try block, and this is a catch block. And here we say that if some error happens, then return that error to the initial peer. If I send this script, then to me, return that error, the last error, to initial peer ID, which is a client. If the client sent this request, then init peer ID will be the client. And this line here, it says that you can access the client through the relay, because the client could be somewhere behind the NAT and behind the firewall, and it has a direct connection with that relay. So to access the client, you have to go through relay. It's really important not to forget to specify your relay. So do you have any questions so far? Let's see if there is a chat. Okay, I see that questions seem to be answered in the chat. That's really nice. So if not, please ping me. So we're going from the theory part of the our event to the workshop part. We already saw the requirements. If you want to follow me. If you don't want, it's okay. If you want, install this, please. So what's the plan for the workshop? We will build a simple service in Rust. It's say here that it's a factual service. What it means is that you will be able to call network. Where to get this text? Here. Great. So then we will configure that service. We will deploy it. We will connect it with a front-end application. We will use CLI to the FLDist here to inspect that service and run scripts from CLI. You can run scripts from front-end, you can run scripts from CLI, or you can use your own environment that you like. Then we will extend that service to be able to write data to disk. And I will also explain how to link several modules together. And finally, we will go to advanced part if we have time, hopefully. And we will talk about authorization that's done through tetraplets. We have this term. I'll talk about it. So let's go to our first little example. Here we imagine we want to implement the DuckDuckGo command that I was mentioning in the chat API part. So what I want to have is a separate service so others can reuse it. And I want to be able to call network, to call DuckDuckGo from that service. But there's a problem with WASM and WASM. They do not provide network socket API yet. But how to work around that? We can reuse existing software. I like reusing stuff, and here we will reuse curl. Not as a library, but as a binary that's already running, that exists on the node. So if you want to do that, to call DuckDuckGo in the CLI, you can just do that command, copy it and paste to your terminal, and you will have some answer that condensed milk is a cow's milk, blah, blah, blah. We will do almost the same, but we will have it as a WebAssembly service that's calling the external binary curl. and return the result for us to use in other services. This is a basic building block that you can use to call any external network API, any WebSocket or whatever. And if you ever need to have not a curl, but some other binary, you can run your own node and put any binary there, and you will be able to call that binary from your node. So how to do that? And what API I want to have? I want to have a simple request function that will be callable from AR script. It will take a single argument URL and return a string result, either success or error. And the whole implementation of that request endpoint, that request function, is here in a single line. It calls external binary curl like a simple Rust, like an ordinary Rust function. It passes a single argument, that's an array of a single argument of a single element as an argument to the curl. So it basically does this. You can also keep these parameters, but then instead of having just this, you will do it like this. It's a simple Rust, nothing specific to Fluence. The only specific thing is that we allow to call external binaries as simple Rust functions. So you can have as many arguments as you wish. Okay. But how Fluence knows where this binary is? We surely shouldn't trust or use path variable, so we specify the path to the curl binary in the module config. So that means that there are module configs. You didn't know about that, I presume. So every module, every WAS module has to have configuration file. If it doesn't need access to file system or the network, it will be just a single field name, nothing else. But here we need an access to external binary curl. And that's why we have to have these field mounted binaries that says that mounted binary curl is expected to be on this path on the node. So let's go to the project actually and review the structure of the project. Here we have several things. First, we have backend folder that contains Rust project. We have a frontend folder that contains a React project. We have a script to deploy the backends. We have a air script to call those backends. And we have this configuration file that allows you to try the service locally. I will talk about it. So let's first review the backend. Right. As I said, it's a simple Rust project that has a single dependency. It's Fluence. It's Fluence Rust SDK. And here, and when you compile that project, you, in result, will have a Webassembly file. So you will have something like curl template.wasm somewhere in the target directory. We'll do that, we will see. So here, what are the sources of the project? They're pretty simple, as was presented on the pictures. Here I pass two arguments, the URL and the options to make it less verbose. Curl by default is pretty verbose, so that will make it quiet but still show errors. And we have this block that says that we have a mounted binary that's available to be called as a Rust function. So anytime you want to call some mounted binary, some external binary, you will have to do it that way. You will have to have external C around it, so it's so Rust knows it's an FFI, frame function interface. You will have to have this link that points was membered module to host. So runtime knows that you mean running those functions on the host. And you will need to have this macro FCE that converts all this and converts underlying types. So you can't have just string in WebAssembly, you can't have just result in WebAssembly. You need to manage pointers and raw memory for this to work. So that what that small three-lettered macro does inside it. A lot of complex logic that you don't have to worry about. You just have to have this macro here. And to describe your public API, you define a function and mark it with FC macro 2. So it converts, it makes it public, it makes it available for scripts to call, and it converts complex structures to WebAssembly format. Okay. So how is it deployed? How to deploy a service to the Fluence? It's pretty simple. The first thing is this, and the second thing is this. Everything else is just a fancy scripting stuff that we don't really care about. So to compile the WebAssembly file, you have to go to the backend folder and run fc build -- release. That's why you need fc installed. So I'm in curl template. I go to backend. I put fc build release, and I have my WebAssembly. I guess it's too small. And I have my WebAssembly file there. Okay. So you can, instead of doing that manually, you can use deploy sh script. You can run it will build, and then it will, that's 2, okay, and it will deploy a service. And once the service is deployed, you will have service ID as a result. So we deployed the service. Let's try to call it. And here, yeah, and sure, where the wasm file, it's in the target folder, so we can check it. It's there. And then this script, the deploy sh script, it uses FLDist tool to create a service. So you basically specify a list of modules as a pairs of wasm semicolon configuration file. And here configuration file we already seen here on the image. It's it. You have a link here to follow if you want. So that already happened. Let's try to call our service. But before that, let's review. Yeah, here is a smaller, smaller version of that script that shows only the main parts. Let's call that service. But first, let's review the script. So to call the service, you use FLDist run air command, and you specify a path to air script, and you specify variables, value for variables that are used inside that script. What it means, variables inside script. So let's take a look at the request air file. Here we have a simple script that goes to a service, goes to a node, which ID is resolved through variable named service. That's why we have here, I will switch tab. That's why we have here this variable that holds a service ID. So yeah, it holds a service ID here, so we can use it. We go to the node relay. Here it's also variable, but run air already gives you that variable to use, so you don't have to specify it all the time. If you switch to another relay, it will be automatically changed. So here we go to relay, where we deployed our service. We call the service by the ID specified as a variable. We call the function request as was specified in the Rust code. We pass this request there, the URL of DuckDuckGo that search for homotopy, what homotopy means. It's mathematical object and stuff, we will see. And we have the result of the curl execution of the call of the curl binary put into, well, variable named result. And finally, we go to the init peer ID, which is the client's address, and we run this thing. This is specific to run air command. So when we do FLDist run air, we have two variables available for us. First one is a relay, and second one is return service. That way, you can always return a result to the client by calling this service return service and function run. It will be just displayed in the console. Let's see how it works in action. So here you can see that it's a different service ID than from what I created, because it was, let me make it a little smaller, it's too big, I think. Hope it's okay now. So we take the service ID we just deployed, we put it here, hopefully it works, yeah, and we get the result. We have the following structure as a result. We have a structure with field error, a return code, std_err, and std_out. Since curl didn't fail, we have an std_out output, and it's a JSON as was returned by DuckDuckGo API. So yeah, now we know that homotopy, it's a term from topology, a branch of mathematics, blah, blah, blah. Okay, so it works. This second argument, so you have here two things displayed. First one is the result of the curl. Second one is the tetraplet that says where this result came from. That's how security works. I will talk about it. I will elaborate on it later. But in short, you have this thing that's called tetraplet. Why tetraplet? Because there are four meaningful fields. There are four fields. From what node this data came, from what service, from what function, and from what JSON path, and which JSON path was used to transform the data. So you know that the data wasn't forged in any way. Okay. Oops. So any questions so far? Let me check. No? So yeah, here's an image of the script. We can also use FLDist get interface to take a look at the service. Let me copy it. Okay, service ID is this. And we will have a JSON structure that describes that this service has the following functions. It's a single function called request with a single argument URL of type string. It outputs string result structure, and that structure, string result, it's defined here in record types. So we know that it has those fields, red code, error, std_out, and std_err, all of them strings, except the return code, which is an integer. And it will also show us who is the owner or who created that service. That's the peer ID that was automatically generated. Here, let me show it. Yeah. Yes. Yeah. Was it? Yeah. client peer ID, that's the one that was used to create the service. And it's the same. So every service knows who created it, and it can be checked in the service function. That's another primitive you can use for authorization. I saw there was a question, right? So yeah, it's recorded, but I will elaborate anyway. I will hope to make it clear that backend is WASM. It's not like a backend is connected to WASM. We have this code here. It says, this is our backend. This is the backend code, right? And this is the API of the backend. This code, it was compiled to Webassembly module and deployed to Node. So it was a really simple deployment process, and you can have it programmed in different complex way. You can deploy different services to different nodes, different backends to different nodes in a dynamic way, however you choose to do. But here it was simple that we have this code. This is whole code of our backend, no more. We compiled it to WebAssembly module, deployed it, and then called this function, which in its order called the external binary curl and returned the string result structure, which has 4 fields. Okay, hope I made it clear now. So if you, it's really kind of annoying to deploy all the time and waste resources. So if you don't want to deploy your service all the time, you can use FC REPL to develop it and test it locally. Here's how it works. You just put, so I was a little ahead of, let me explain. So here we have a simple TOML config that describes for FC REPL how to run that service locally. Here we have a specification for a module. It's almost the same as you have seen in JSON, right? It's almost the same as a configuration for this module. Just this is in JSON and this is in TOML. It specifies where to look for the module. It specifies the name of the module. Yeah, so we had our module at this folder, right? Under this name .wasm. That's exactly what it says. And here we specify the same mounted binaries. So we tell that the FC REPL should look for the curl on my system. Now it is running locally under this path. So let's run it. To run the FC REPL, you have to specify path to the configuration file. You run it. App service is created immediately, and you can call it. Let's see how we can call it. So it's really simple. You just basically it's almost the same as in the air script. You call the different thing is that you specify here not the service but the module name, and you specify function name in the argument. Let's do that. Yep. And here we have the same output. Well, not the same. In this time, it's about condensed milk, not hamataki. But still, we have the output. We have this object that contains the fields that were the same in the previous call, and we have the result from DuckDuckGo forwarded here to my console. Okay, so it works. Nice. That's how you can experiment with your services locally. And you can have in this configuration file, you can have different modules, I mean, several modules, different modules linked together, and we'll see in a moment how to do that. Okay, so but first let's take a look at how to connect the front-end application to the curl backend. Let's go to the go and see if it works. I'm going to the front-end directory. I already done npm install, but let's do that again. Maybe I shouldn't have, because it takes time. And I don't have much of it. Too bad. Anyway, let's review package.json for now while it installs. So package.json, I hope you know that it allows you to specify dependencies for your project. Here there are two main dependencies for using Fluence. First one is Fluence JS SDK. Second one is a library that allows you to switch between different environments of the Fluence network. Okay, it's done. Let's start it. Hope it works. Would you like another? Yes. Oh, I guess I already have it. Anyway, I already have it running somewhere. So here we have a really simple web application that has the field to enter the URL and the button to issue a request, to issue a call function to the service. We will go through the source of the front-end application in a moment. Here you can see that we sent a request to DuckDuckGo and received the same response. So if I put here another string, we will have Apple disambiguation, definition, text, Apple daily. Well, it's not that good as for homotopy, but still it's we have called DuckDuckGo and received the response. It's a really simple application, as you can see. There's no UX there. So how that application works anyway? It has three main files that I care about for right now. The first one is package.json that specifies the dependencies on Fluence JS SDK, but that we already looked through. The second one is Fluence.ts. It's a TypeScript file. All it does, it gives you a single function to call. It's called curl request. It accepts Fluence client as a connection to the node, URL to call, and TTL, meaning that if this request hasn't been executed in this number of seconds, then it should fail. And here we have the script. It's really easy, almost the same as we used with run air. But since we don't have relay variable provided here by default, we have to provide it our own. So it does almost the same. We go to the relay, we go to the node that hosts service. It's the same thing in our case, but still you can have it different. You can have work with different nodes through same relay. And we call service, we call the function request there, we put URL, we get result, and we finally send a result back to ourselves. Right. Here we could use init peer ID in person science, but we decided not to for no apparent reason. It's just a matter of taste. How you like it, you can write it. And here you can see that result is returned to the client through relay. So it's expressed in this way. It says that sequentially go to relay, do nothing there, op identity just nothing, does just nothing. And after relay, go to client and call callback function, callback service with callback function. And callback is defined here. It's done to disambiguate with, so you can see that callback ID is generated on each request. That way you can differentiate between different responses to different requests. It's all up to you how to do that. You can express any business logic or any logic of any application with that. So what we have in result is a curl function that returns some result here by sending the script with that data to the network. Script and data, they are wrapped in a structure called particle. Particle is a network packet that contains, well, script and data and the timeout. And once, and network will start executing the script line by line. And once it goes to that line, the particle will be sent from the relay to the local client and will be executed in a local WebAssembly runtime. So this front-end application, this one, internally it runs Webassembly module to interpret that script. And once it receives the script, it sees that all those instructions are already executed, and this instruction belongs to the local client. So it calls the callback. And the last meaningful file that glues this all together. It's a simple React application. I'm no front-end developer, but this is simple even for me, who has no experience whatsoever. So what happens here? First, we connect the client to the node. We have relay node defined in the Fluence.js file. Let me show you. So relay node is a third node from testnet environment, and environment comes from Fluence network environment library. You should use testnet environment always, but this index you can switch. You can use several nodes. You can use all of them. I think there are like 10 of them right now. You can use any other, or you can stick with this one. It's the most used node we have. I will show you that also. So we have relay node. We connect there through create client function that we take from Fluence.js SDK. And well, we basically set the client to use it later. So it's really obvious. And then we execute curl request. Once this request function is executed on the button. So we have this button, and on click it just executes request function that in its turn executes curl request, which in its turn sends script to the node. And it returns promise, so we wait for it. And finally, we set the data to be displayed here. You can see that we access stdout field. So the data, the structure returned from the Rust, right? So we had this, we had a structure returned from Rust, and it had some fields, and those fields, they are deserialized to JavaScript objects, to JSON objects, and you can access their fields in a simple way. Later, it will all be smoothed out with, it will be all, will all have types, proper types, so you couldn't use wrong field, but currently you have to be careful about that. But I think that's the nature of the JavaScript and TypeScript, that you know that these are dynamically typed languages, so you have to be careful about fields of the structures anyway. Okay, so front-end works. We have our first, we just had our first backend implemented, and we made a front-end app for it, and it can implement this /DuckDuckGo command of our chat, and you can start right from there. You can start developing your app right from there, and with a few customizations, you can already hit those bounties, the first two. Just be sure to customize your apps to do something different, not copy-paste the existing code. Okay. Any questions so far? Seems like no. I hope there are still people watching me. But anyway, this all will be recorded, so you will be able to watch that on YouTube, I hope, or somewhere. So you will be able to use that video as a hand of help through the workshop. And we have documentation also to assist you, so I'll talk about that. Okay, now, as I promised, let's extend our service with ability to write files to the disk. We can use familiar functions from Rust standard library, from stdfs, the read and write functions. They just work. You don't need to have any external binaries or stuff. You can just use standard library functions for that. So now we have, we will have an application that's called URL downloader that uses curl to download something from internet, some file, and we will use local storage to write that file to the disk, right? And that makes 2 WebAssembly modules. And we will have the second WebAssembly modules to provide the public API to glue those 2 modules together. So let's first, the main focus here of the URL downloader will be on local storage.was, because it's a new functionality that we extend the previous one. But you should also know that this is not a different name a little, this is just a convenience. Never mind, it doesn't mean anything. So here is the local storage file, the main code of the local storage module. It does a simple thing. It takes a file name, it takes file content as a byte array, it creates a path. It will always write all files to the same directory. This is for simplicity purposes. And then we just write file content to the file system, and that's it. And if we have an error, we return it as a string. You can obviously define your own structure with different fields to return error as a separate field, as you would do in Rust. But here we return it as a simple string. And if everything is okay, then we return okay. So get follows the same logic. We have a file name and we return byte array. We construct path from file name and we just use fsread to read the contents of the file. And if something goes wrong, we return error instead of file contents. It's not the best way to approach error handling, but it's for simplicity purposes, it's really okay. We will see the error, so it's gonna be okay for now. But you can approach that differently. You can use your favorite Rust patterns here, except you can't use enums right now, but the FC macro doesn't support them, but everything is still expressible in terms of structures. So that's the whole logic of our new wonderful functionality of writing files to disk in a peer-to-peer network on a distributed/decentralized application. So our app here, it won't be much distributed. It will be a single app, but we will later see how to make it distributed application and compose different modules as different services into a single application through AirScript. But first, let's start with a simple approach where we have all these modules linked together. Let's review the Facade module. I'll go to examples repository. Then I go to URL downloader folder. And here I have Facade module. It's a simple module. It has simple dependencies, Fluence SDK, log for local development, and base 64 for, well, deserializing and serializing file contents to string. It's again a single file here. It could be, it shouldn't be just a single file. You could use any number of files you want. So this is a Facade module. What's a Facade module? The thing that I didn't tell you yet about Fluence applications is that you can have only a single module to be publicly available. That's for security reasons and for, for designing reasons. When you design some service, you want to provide nice API to your users. You don't want to show all API uncontrollably, right? You want to have some control over it. And the Facade module, it gives a control of it. So only single module has its API publicly available. If you need to have API from different modules publicly available, you can just repeat it here. You can just here define function and call the internal module here. So we have two API functions. First one is named fancily get and save. And it basically returns OK if the file was saved. So first it accepts URL and file name. So it downloads contents of the file or site or whatever through the curl, returns result, and the result is saved to a file, as a file. So here you can see that we're using the same stdout field that was before. That's because we are using external binary. And if it's not successful, if download is not successful, we return error and we will log error. This log message will be seen through FC REPL. If you develop your services on FC REPL, you will see this log message. So that's the first API, first function that we have in our API. The second function is a load file. You specify file name of the previously saved file, and it returns it as a base 64 string. Pretty simple, right? You download, you store. If you query already downloaded file, you just get it from the file system and return its contents. The crucial part here is how to link several WebAssembly modules together. Here we have the curl adapter. It's a module around curl. It's almost the same as in the previous example, but it has a little different signature. It has download function that returns result containing. We'll look through it. The difference is that it returns result as bytes, not as string. So okay, and here and we link the curl adapter to the Facade module in almost the same way as we did with mounted binaries, but with this crucial difference that instead of specifying host here, we specify the WebAssembly module name here. And the same with local storage. We specify local storage module name, and we say that we want to use get function with the name file get. We want to use put function with the name file put, and that's it. So we're free at renaming the functions as we want. I didn't want to have get and put functions here. I wanted to make it clear that this is a file put and file get, and I did that. This is through this link name attribute. So far, so good. So let's take a look at the curl adapter module. It should be really familiar to us already. It's almost the same as the previous module. The only difference is that instead of previously we had this function request and it was stringifying the results. So it was trying to convert std out or stdr from byte array to string. The download function, it doesn't do that for performance reasons. Obviously, you don't want to convert bytes to strings with no reason. It's handy for returning to the front end strings, but between modules, makes more sense to return bytes. So the difference is stringify and no stringify here. So in everything else is the same module as before. It has the curl mounted binary with it, so it has to have configuration file for that module. And we can see it, that we have this configuration file for curl here, and it's the same as before. It specifies mounted binaries. And let's take a look at the configuration file for a module local storage. It's different. For some funny reason, it has mounted binaries here. It makes no sense. They don't break. It doesn't break anything, and it just it's unused. So ignore that. It's a configuration for a local storage module. So we need to have access to file system. And here how it's done. We need to specify preopened files, and we can only use temporary folder and directory, and we say that we want to refer to the directory under the name sites. So here, if we take a look at the local storage again, we will see a constant defined here, the directory, and it says sites. So you can kind of abstract here over the real path that will be used. It can be handy in some cases. So instead of linking sites to TMP, you can say that you link sites to different folder. Okay. I thought someone wrote me something about workshop, but no. So we have this project with 3 modules: curl adapter, local storage, and facade. Now let's build it and use it in REPL. So let's build it. And let's do fc REPL, REPL config.toml. And here we have it. Let's take a look at the commands prepared here. We can call get and save function to save logo to file system. Let's do that. And we can see here and we can then load that file from the file system in base 64. So as all this is happening, since it's a REPL, it's a local thing, all this happens on my machine locally. That means that the file is stored somewhere on my machine. Let's try to find it. I'm not sure. It's here. Logo SVG. Okay, well, it's a SVG file, but let's open it in a more good fashion. Yay, it's Fluence logo. Okay. Oh, wow, I have 9 questions. Okay, That's good. That's a good conversation we have there. So what just happened? We have built the project into 3 Wasm files. If I go to right here, I will see Wasm files. It's more than 3 because the build sh, it builds files like here and then copies them to artifacts folder where, well, it's more handy that way. Okay, we built it and we used REPL to run the service locally. How it works? We have 3 modules described here. First one is local storage that describes pre-opened files and mapped dirs almost the same way as before, except it uses current directory instead of TMP. It describes curl adapter and specifies mounted binaries as before, and it describes Facade Module with no access to file system or network whatsoever. So Facade on its own, it can't access file system, it can't access network. Only local storage can, only curl adapter can. Okay. Так. Well, so we can also deploy the service. I will spare myself from doing that to save time, but it's anyway. We can call it from CLI the same way as we were calling the previous service. Let's review the script for the. So I just executed download.air script here with service ID specified to some previously deployed service. I can deploy again and use this the service ID and it will work. So what's inside download.air? It's this. It says that go to relay, call the service, call the function get and save, pass their URL to logo. Here I shorted it just for brevity. Save it as logo.svg, then go to the service and call function load file and read file from logo.svg, put it to variable name bytes as a base 64 string and return to the client. You can define any service that converts from base 64 to base 58 or whatever. You can put any adapters or converters services as separate services, and then you can send bytes there for some, for example, for compression. If it would be like a JPEG, you can compress it and return compressed files, all in the network, all without returning responses to the client until the very end if you need it. You can avoid returning bytes to the client whatsoever. You can just take bytes from the file, compress it, and upload to S3 if you are to write S3 adapter on Fluence. Please do. No one has done that yet. So that's a good idea to have a storage, S3 storage engine available to call from Fluence. That would be nice. And it's totally possible to compose in that fashion. Okay. Everything of this I already showed you in the code. So the most interesting part, as we are approaching 2 hours already, and I still haven't came to authorization. So composition. Imagine that so what we did, we have linked 3 WAS modules together to make a single service. Was it required? No. You could easily, or your friend, develop a local storage service and deploy it. And you deploy curl adapter service, develop and deploy it. And then you can compose those 2 services. Here I have an example script of how to deploy this as separate services. So here we build WAS WebAssembly files. we don't use Facade anymore because we deploy first local storage, and the local storage that was, it will be the Facade module. It will be the module that faces the public API that's available to call from script. And we deploy curl adapter in the same fashion. So this is the single module in a service. Before it was a service of 3 WebAssembly modules. Now it will be 2 services, each of them with a single WebAssembly module. The API will be different, right? Because before it was get and save function, but now we will have to deal with the with the API of the modules themselves. So in curl, we have the function download. In storage, we have function put. And we do the same thing. It didn't change much. The script, it's almost the same. But before you were using this API and then load file. Now you're using the API of specific modules. You call curl download to get contents as bytes, and you pass those bytes to storage put. The same thing that let's take a look at the Facade module. Hope it's here. No, it's not in the picture. Sorry for scrolling around. So again, what I want to show you is that this air code does the same thing that we were doing in Rust in the Facade module. Let's take a look. So here we have this get and save function, right? What it does, it calls download on curl module, then it calls put on the local storage module. We here doing same thing, download and put, and then get the same as we were doing through load file before. But now anyone can reuse the curl service and storage service for their purposes, right? And it didn't change much. We split our kind of monolithic service into smaller parts and provided them as separate APIs. Isn't it awesome? You could do the same if you work at a company and you have developed some API over S3 or over Mini or over whatever, and you can give other people access to it through the WebAssembly adapter that will simply call it through curl or through locally mounted binaries if it's a daemon. Whatever you can give other people access to your API on the same protocol. So imagine if a lot of people develops a lot of services and you can compose over that. Imagine if Spotify gives you access to your listening history and you have a service some AI service that can consume that history and give you back some analysis of it. You don't need to have API integrated into this service. You just have to know the format that AI service understands and how to convert Spotify format to there. You could express that conversion of formats, for example, from JSON to XML or something, as a WebAssembly service. And you can deploy it and others can use it. And you have deployed a small WebAssembly service that all it does is converts data from Spotify to some analysis, preference, music analysis service format. And now not only you can enjoy the analysis of your musical preferences, anyone can. Isn't it just amazing? Imagine if the whole internet was working like that. Okay. Any questions whatsoever? I mean, so far. Okay. Yeah, you surely can ask any questions on Calendly. You can book a call with us, with me, with our team, and we will discuss your idea and help you architecture it, help you approach the solutions. Yeah. So, okay, maybe my previous words about anyone having access to any IP frightened you, because, you know, if anyone can call the storage put API on my computer, I wouldn't be really happy about it, because one morning I get up and I see a terabyte file put into my MacBook, and it has not so much gigabytes left there, and I have no free disk space, and it's and it could be worse than that. So we have to protect our APIs. We have to manage the authorization. We have to be able to say that these people can use this API and these people can use only this API. How is it done? We already seen the tetraplet. But okay, I'm going too far. So the first thing, every service internally has an access to this function. You can always get call parameters from any service in any function, and you will get security metadata that will contain information about why, where something happened and everything scrolled. You will have information about who sent the request. That's init peer ID, as we see in person science. You will be able to know who has created the service, who's the service creator or owner. And for example, this way you can do a check against if the current color is an owner of the service. But you have more info than that. The get call parameters function, it returns the following structure. It has the following fields. So the current call initiator, the current service ID, if you need to check against it, for example, if you want to check that it wasn't redeployed or something. The ID of the service creator, so you can know who created the service. The ID of the current peer that hosts the service. So it's basically the ID of the node that you have deployed the service to. Current particle ID for deduplication of requests, to be able to implement exactly once semantics, for example, to be able to make idempotent queries and stuff. And the most crucial, most interesting part is tetraplets. So imagine we have implemented this function is owner in one of our services, right? It returns a Boolean, true or false, no information about whether, no signatures, nothing. So why trust that information? Imagine we have a script that calls isOwner and returns and gives that information to other function. Would you believe it? Like if someone gives me, I am the owner equals true, and that's the authorization. No, because that data could be easily hijacked, right? Anyone can emit a true result into script. I can put true into data and just feed here a true value without going to isOwner, without calling this owner function here. Okay. So why believe it? How to make sure that this value, this true or false, comes from the correct function on the correct service? Okay, I have 20 minutes left. I will do it in 20 minutes. So here where tetraplets come into play. So for each argument that is passed to the as an argument to our function, for example, we want to extend storage put with check of authority, to check that the only owner can write files to the file system, for example. Then when we do this, when we call put function with those three values, for those three arguments, the following happens. With each of the argument, we have a corresponding security tetraplet. So for each of these values, we will have a single tetraplet that says where this value comes from what node, from what service, from what function name, and was it modified in any way by JSON path. This way, what we can do, we can store the information about which function to believe. So owner can set the following information, that storage put should only believe true or false coming from the auth service on that node from the function is owner and without any JSON path applied whatsoever. And if we are to call the storage put function with those arguments, we will see that we have this tetraplet, that this data comes from that node, from that service, from that function, and it wasn't JSON path applied whatsoever. So, and we can implement is authenticated function. So we can implement put function in this following way. We receive is owner, right? And we call is authenticated, passing a simple Boolean value there. And if it's not authenticated, we return simple false, meaning that put didn't succeed. So inside the is authenticated, we get the security net information. We get the first tetraplet for, we know the first argument to the function is owner, is owner. And we check that this tetraplet is correct, that it's a correct service ID, it has correct function name, and it has no JSON path applied to it. This thing is implemented in the project called Fluence. It's a CRGT-based editor where you can sync different the text between different tabs, like this. You can open this link with your friend or in several browser windows, and it will sync the contents. So inside, it uses the following logic, almost the same logic, to authenticate users. So only owner of the service can add users to that editor, right? It makes sense if I don't want anyone to do anything with my text that I myself deployed and I editing it with my friend. I don't want anyone to interfere with that. So let's try to see it in action. Let's go to Fluence.
Alexey, I just thought I'd intercede there because we have actually we have a hard stop at 7:30. So
okay,
my thought was that maybe there's, because since there are still people in the audience, you'd like to share a link and continue the discussion there. I don't want to kind of
maybe end here with going through documentation. Do I have a few minutes?
Yeah. It's just you've got 5 minutes basically.
Okay, okay, 5 minutes. Great. So cool. I will do that in 5 minutes.
Cool.
So go to Fluence services README, follow it, and deploy services on your own and see how it works. You will see that in order to use the Fluence app, you have to first set tetraplet. So as an owner of the Fluence, as one who deployed it, you have to say to it which data to trust, which JSON path to trust, which function is correct, which service is okay, and so on. You have to do that. So the service knows who to trust. Okay. And well, if you, and here, after you've done all of that, you can try it by running add message scripts, and you can just follow README here in the services of the Fluence. It tells you can just follow the steps. So if you are to use a wrong JSON path, for example, you will have the following error, that JSON path was expected to be like that, and JSON path actually was like that. So if data is forced from in some way, or it comes from a different source that you didn't allow, it will fail. You can check against it. You can check the authenticity of the data, its origin. It kind of like a cross-origin request policy. That's what we were inspired by. So it's kind of like that. Okay, so the network is live. We have a dashboard that shows all the services running on the nodes on the testnet. We have documentation here that overviews the language. It overviews how to develop services, how to launch your own node, the structure of the language, what built-in services you're able to use. There are plenty of them. It talks about the authorization in detail and explains different things. It has extra resources with YouTube talks and stuff. It has links to our Telegram, to our Discord, to the dashboard, and to discussions on GitHub. Please use it. It's a really nice way to discuss and to share your knowledge, to reuse knowledge. Reusage is the point of difference. So here's the dashboard. Dashboard contains a few of the future blueprints. It shows nodes that are in the testnet. You can see that I was saying that the third node is the most used one. You can see that it has almost 400 services deployed into it. Okay, so play with it, look for it. And we have a lot of examples in the example repository here. You can find all of those links in this link. I will post again in the Zoom in a moment. And well, play with the Fluence. Develop on it, hack, create Calendly calls with us, join the Discord, join Telegram. That's it. I'm done. Let me start.
Awesome. Thank you very much, Alexey, and for the rest of the Fluence team for helping out with the questions in chat as well. Yeah, this video will be going live on the YouTube. So hello to everyone still watching on YouTube. And that should be up tomorrow. I guess just to round off, we have obviously the Stellar event on Friday evening, starting at the same time as this one did. And then a couple more events next week, including a general introduction to blockchain, the Skynet workshop, and the Vega workshop. But thanks again to the Fluence team, and we'll see you all in the future.
Bye-bye. Thank you.